Hey there, welcome to the course. We are going to talk about GPU programming, and this is our instructor, Kaham Suraya. So, it is essential in this modern world to know the GPU programming, especially if you know that this is the very much driven market for a technology stacks when the AI is emerging. So, let's see what we are going to cover in this course. So, here we're going to cover the CPU architecture, GPU architecture, and interaction with the CPU and GPU, and followed by how we will be starting our GPU programming and what would be the stack and the choice that we are going to opt. So, here comes the CPU architecture. So, the CPU is typically designed for a general purpose. Hence, its typical core would be 6, 8, or up to 64 cores. And it's designed for a serial processing. That means you can actually use it even for a task parallelism because of the multiple cores which are existing on the CPU. And as you can notice, there would be very low latency for the CPU. So you will be actually parallelly executing your task like listening to music, opening a text, chatting to someone, or capturing a video, capturing a recording, playing some background videos, surfing on the web, and lot of other tasks. Now, all these tasks are parallelly executed, and each task is carried out as a serial task, and that is very low latency. Like you are getting your response time as quickly as possible, and majority of CPU area is designed and occupied with the cache and the various controls. Now, as you can see in this diagram, so that is a chiplet. On top of that there would be a fabric which would be interconnecting the all the controllers and the components, which would be the CPU core, which would be consisting of a basic arithmetic logic unit and the cache. Then there would be a internal graphics card which would be GPU controller. Then there would be PCI controller which would be communicating with the devices external, which are the discrete graphics card or NVMe SSD, which are the storage, or many other applications. Same way, there would be a display, there would be a camera. This various controller would be connecting you to the external world of an interface, which are exist on the CPU to how to control all these various external user actions. And the core component is a memory controller, which would be controlling the DRAM, which is the core memory. So whenever there is some data which needs to be processed, it needs to be stored, it needs to be fetched, it is all coming from the DRAM. Now, this happened to be CPU architecture. Now, there would be a GPU architecture. Now, if you notice, it's a little bit of a complex, but there would be a PCI bus which would be connecting to the GPU, and this is a very simple and most efficient block diagram where you can notice that every GPU typically would have a scheduler which would be getting the instruction received from the programmer, and then it would be allocating the instruction to perform a set of tasks over the different execution unit, which are streaming multiprocessor, and within that streaming multiprocessor there would be dedicated cache and local memory, and there would be a global shared memory which would be used by all the streaming multiprocessing cores, and through which that data is actually coming from the CPU. So we will be transferring our data from the local storage or DRAM to this GPU global shared memory in order to instruct our GPU to program and execute the certain amount of operation which we desire. Henceforth, you can see that with this architecture, GPU is highly effective for a parallel processing, such as data parallelism, where you have a single set of a data and you are executing an instruction which would be similar kind of operation instruction over this data. So you are exploiting the data parallelism here. And as you can see that there would be a hundreds and thousands of cores unlike the CPU. That's why you can parallelly execute all this instruction such as a matrix multiplication, matrix additions, or many other independent tasks which you can actually execute in parallel without having to dependency or deadlock. Now, when you see as a whole architecture from programmer point of view, you will see as interaction between CPU and GPU as in this diagram. Now, as you can see, PCI bus is a component which is connecting both CPU and GPU via PCI controller. And here, whenever there would be instruction which we wish to pass, we instruct our CPU to pass on this information in the GPU global shared memory along with the instruction which would be present in the scheduler, and the scheduler will schedule all the instruction which are in this GPU pipeline and start executing one by one. So once the instruction is fetched by every individual streaming multiprocessor, it will execute the operation, it will cache and store in its local memory and report back results to the global shared memory. Now, we will wait for our instruction to complete all the computation which would be done in the global shared memory, and once that data store is updated, we would be collecting back that result and storing it into our DRAM. So that would be the flow. So we will be sending a data and the instruction and collecting back that data. Now, this is the additional requirements which is differentiating the GPU programming with the traditional programming. In the traditional programming, you just write a program to do a addition of a matrix and you can just simply just do it, and you can leave rest up to the compiler. Now, when you are using a GPU, there would be a different GPU by different variants of a brand, and there would be different instruction set. So each and every vendor provides their own unique API collections which you can use and exploit the GPU for your data parallelism. Now let's figure out what are the choices we will have when we will be picking to the GPU programming. So there are three major vendors when we hear the name GPU programming. You can work with the NVIDIA, you can work with the AMD, or you can even work with the Intel. Now, for each and every vendors, there is a different programming stack through which they exposes the various optimized libraries and the programming SDK stack, which will be called as software development kit. So, as a programmer, you will not need to worry that how they are optimizing their own compiler to efficiently execute your program on their hardware. You will be just using this toolkit. So, from the programming stack, the toolkit which you will be using in the NVIDIA, which would be CUDA SDK, in the AMD, it would be the Occam, in the Intel, it would be one API. And for all these respective SDK, the last row consisting of the hyperlink of the official link to the tool, and you can go and download and follow the rest instruction, which we will be covering in the upcoming session. Now there are instruction processing unit, which are streaming core and the streaming processor, which are the terminology used by the NVIDIA, whereas AMD would be using the terminology as SIMD lane, and Intel will be using the terminology as a processing element. And the building block which would be known as the execution unit, a core. As in the CPU, we would be noticing there would be a core which would be calling the CPU. The same way, here we will be calling it out as a streaming multiprocessor. So in NVIDIA, it's like a CUDA core. In the AMD, it is a computing unit, and the Intel, it is called as a Xe core. So these are the choices we have. So irrespective of the course we are picking, you can actually choose yourself the variations of this hardware devices, and you can choose any devices which you have with your own. This all the vendors having the same APIs we will be discussing forward into the upcoming course, and you can use either of them to execute the task and learn the GPU programming. The brand or vendor or difference in the API should not block you, and you will be able to perform the GPU programming on any of the GPU you have. Thank you.